Right, so in today's video we're going to have a look at Heap Sort, but in order to really get to grips with this sort we need to understand heaps first. So I've done a little presentation that we'll go through just to have a look at how heaps work, and they're not really scary at all. It's just a different way of thinking about how data can be structured. So let's have a look. What we do is we take a data point, and that data point can have two children, a left child and a right child. And this, the top data point with the blue circle, is known as the root. And it's very little different to forming a binary tree, where each node can have at most two children. So this node will fill up the next generation from the left, and it will have the left child, then the right child, and if there's any more, so if we had up to 6 data points, then we would add an extra one to that right child. And this is known as a parent because it has children, and these are the children, or that's a child of that parent. Now it can get a bit confusing because this is also a parent because it has children, and this is one of, or a child of that parent. But the child in this instance isn't also a parent. It has no children, and that becomes useful later on. So let's put an array in here and have a look at some numbers that we need to sort. Now in this list we've got 10, 48, 1, 9, 21 and 6. And these are each at certain index positions. So let's have a quick look at those index positions. 0, 1, 2, 3, 4 and 5. And that corresponds to positions within this heap. And this heap is just, it's an imaginary concept that helps us to work through data in a non-intuitive way that's actually very efficient and powerful. So we can place the indices along this heap like this, where we have 0 as the root up here, and 5 being that end one right down here. It's the last thing we add in. So we're just adding things in from left to right, going one thing, two things, three things, and if we had a fourth it would go here. And then you'd start back over here and you'd add one here, and so on, continuously. And this enables us to do something really counterintuitive, because you might be thinking, oh, I'll have to code something up to create this structure, like a node where it declares two children and it will keep a log of a parent. You don't. We can just use an array, because if we look at any parent position, so let's take the root at 0. If we wanted to find this left position, it's 2 times the index of the parent, so 2 times 0 plus 1 here. And if we looked at this and we wanted to find its left child, then this would be 2 times 1, 2, plus 1, 3. And you can see how this is related. So the 48, its left child would be the 9. And it gets even better. The right-hand child is just plus 2. So we can access, as long as we know the parent position, we can access the two children in an array, in that linear structure. So we don't have to store it in any form of complex tree. We can just store it in a list and access it as though it's a tree. So what next? Let's put the numbers in, and you can see that they just populate the positions where the index was. That's where the number comes in. So 10 at 0 and 6 at index 5. Now, I've just done a cheeky little thing here where I've renamed this array, because when we're coding this up, we're thinking about this structure, we're thinking about how we can organize it into this binary tree, but it doesn't actually involve us coding anything different. So all we've done is set the name of this variable, or we've set heap equal to exactly the same array, because we're going to treat it like an array. You can get a max heap where you want the maximum number in the whole heap to be at the root position up here, or you can do a min heap where you want the minimum number to be up here. And we do that by carrying out a very simple algorithm. we get every parent, so this one and this one and this one, to look at its children and decide if a child is bigger than the parent. And if so, it'll swap. And we always start from the furthest child, so the lowest parent. Now we don't need to look at the children because they don't have any children to compare. So the lowest parent would be this one here at index 2. So we look at this value and we say, well, that's 1. Is 6 greater than 1? Is this child greater than that? It is. So they swap places. And so we now have 6 in position 2. We go over to the next one and we say, okay, so over here, are either of these two values greater than 48? No. So we don't change anything. And then we go to the index position of 0 and we say, okay, looking at 10, are either of its children greater? Yes, this one is. So they swap places. So we've done this change, but we have something now that's changed a lower level. So this has now changed. Now we don't need to look at any of this here to assess whether this 10 results in a difference to occur here. So we'll just ignore that. We'll get rid of all of that chunk. And we're going to say, let's do another version of a heap where actually this 10 is now sort of the root position. And we want to see if any of the children are greater than it. And you can instantly see, obviously, the one at index 4 is. So they swap places. And that's it, that's done. Now, of course, what you can do on a much bigger heap is you iterate this process down. So you can work down a tree, but you're ignoring a huge amount of your data because you don't need to look at it to carry out this calculation. And that's what can make this algorithm so powerful, because you don't need to use all your data all the time to get each value. You're being much more strategic about how you use your data. So we can now pull the rest of the thing back in, and we have what's called a max heap. Now, a max heap doesn't mean every number is organised, but what it does mean is that at every parent position, the parent is larger than either of the two children. So we have a max heap. And that's just described down here, and it's an array, because we were just working with this array. This is a nice visualization of what's happening, but this is what it will look like in the code. And then what we do, well, we want to get this value out, because we know that's the maximum value in the whole heap. So we want to take him and put him in our sorted array. So what we do is we carry out a swap. We take the lowest position here and we put it to the top, to the root position. So we go from index 5 to index 0. And then we pop the 48 off and put it into the sorted array. So we now have a smaller array that we're working with, or a smaller heap, and we've got one value nicely sorted. And you can probably see that as we iterate this, in fact, it sort of starts to self-sort a huge amount of the data, so a lot less processing is required. There's a couple of interesting concepts, though, that we want to just pick out here, which is, in a max heap, large values, we kind of call it bubble to the top. They work their way up to the top, and small values sink to the bottom. And so we can use that to sort our numbers. Now, if it was min, it would be the other way around, and small values would bubble up and large values would sink. So what do we want to do now? Well, we sort through this, just like we did before. And you can see that the 21 and 1 switch places. And I should have said as well, because we don't actually have many parents anymore, just these two. They're the only ones that are parents. And so again, when we come to here, a bit like before, we just consider this little setup, and obviously both children are larger than the parent, so the largest one switches place. And we get that. And so we have another max heap. And we can keep doing this, where we'll take the 21 off, or we'll switch places, so the 1 goes to the top, The 21 goes down here, and then we cut this off. We prune this off and store that number in our sort. And we can just keep iterating this process until we have a fully sorted array. And it's very efficient because we're only looking at certain chunks of data at a time. You know, if we go down the left side, we're completely ignoring the right-hand side of the tree. And that's a huge amount of data being ignored because we just don't need to look at it anymore while we're doing this calculation. And it's a very, very efficient route to sorting numbers. So, let's code this up. So you'll want to grab your favorite IDE, and in this case I'm going to be using Sublime, and we're going to just code this up. We're going to have a work through each of those steps and make a little heap sort sorting algorithm. So let's start by just adding a little comment into this program. So let's just start by defining heap sort, the function, and it will just take an array, nice and simple, or a heap, that we're going to want to sort out. And so what will we do then? Well, we'll say that our sort array, we'll declare it right at the beginning, and that's empty. We haven't sorted anything yet. And our heap will equal a copy of the array. And that's just basically the same as what we did in that little presentation, where we just renamed it so that we now have a copy of the array that we're working with, but that's our heap. And we're going to say that while heap, so while there's anything in our heap, we keep running this program because it's not finished sorting yet. So while heap, we want to create the max heap, or you could also create the min heap, but to be quite frank, it doesn't really matter in this instance. If you sort them by max and you want the smallest first, you'll just reverse the list. So what we want to do is we want to iterate across the parents, and we want to do it by reverse in the heap, so that we go from the smallest parent first, or the lowest index parent first, and look at its children, and then the next one look at its children, and so on, like we did in the little presentation. So if we want just the parents, and we know that the root has 2 children, and then those 2 children have 2 children, and so on and so forth, then the number of indices that will be for parents will equal the length of the heap divided by 2. Oh, I've done something wrong here. Minus 1. And let's have a quick think about that, okay? So if we had 6 values, like we did in that PowerPoint, there was the root that was a parent, and there were the 2 children that were parents as well of the root. So that's 3. Now, the length of that list, the length would be 6, and we would divide it by 2, which would give us 3, minus 1 give us 2. So you might go, well, that's only given us 2. But in Python, you count from 0. So it's 0, 1, and 2. So it's 3 indices that are being checked, or index positions. And we'll see how this works a little bit later. And we're going to want to go to 0, so we need to go 1 less than 0 because it's going to go in reverse, and because we're going in reverse we have to use minus 1 as well. So this is just a little simple range function. Okay, and for each one of these instances, for each of these parents that we're checking, we're going to want to do this tidy heap function. So I'm just going to call it tidy heap, and we're going to come back to this in a moment and have a little think about how we're going to work through each heap to sort those numbers. And I'm just going to have a little think here, because if we've created the max heap, then we know that the thing at position 0 at index 0 is the largest number. So we can do that process we demonstrated in the presentation where we swap the largest number for the n number on the final index, and then we take that final index off and add it into our sorted list. So let's just take the sort array and tell it to insert at 0 position the heap value of 0. So it's taken the largest number and inserted it as 0. Now, because I've done insert, this will actually organise the numbers from smallest to largest, because each max as it goes down will get inserted at 0, and that's one way you can work around the order that you want things to be presented in. And then what we want is the heap at position 0 and the heap at position -1, so right at the other end, to equal the heap at position -1 and the heap at position 0. So they basically just swap. And then we can pop the end off. So that's the largest, the maximum number. We've stored it in our sort array, and then we've popped it off. So our heap is now a bit smaller. We'll eat away at the heap until there's none left, and then we'll exit the while loop. And when we exit the while loop, we'll want to return the sort array, and we'll just put a space in there so it's a little bit tidier. And we could add a comment here, I think. Storing the max value in the sort array, just so that we know what we're doing with this step, and that we're sort of removing it, we're reducing the heap down. Okay, but we've got this bit to code up, and this is really where the brains go on, those steps that we were looking at of how things are compared. So let's get a bit of space in here, and we'll say it will define the tidy heap. Say heap, and we'll also have an index position, because can you remember when we had moved the 10 down, we then wanted to compare it like a small heap, like a mini heap, rather than looking at the whole thing. Well, we can use the index position to effectively ignore the rest of the heap and just have a look at that section of the heap, or all the children down from there. So that will be very helpful later on. And we define the left side, the left child, as equal to 2 times the index, so the index of that parent, plus 1. And the right was basically the same, except it was plus 2. So we're able to use this array to keep an eye on the left and right child of a parent based on its index. We can define something called large, and it will be equal to the index. And what we're going to do is use this large as basically a tracker to see if we have to switch round the child with the parent. So if the left value is less than the length of the heap, and that's just saying that as long as we're still within the bounds of the heap, because obviously if we get to a child that has no children anymore, and we do 2 times the index plus 1, it will give us a number, but that number won't be within the heap because it's not there anymore. The heap's smaller than that. So we have to just make sure we're still within the heap, and that the heap large, so that's the heap at this index position, is less than the heap at the left position. If that's true, if that's all true, so I'm going slightly off because of the font size increase, then we want large to equal left. And then we want to do a second check, and it's very important, this isn't an elif statement, this is a separate if statement, because we're wanting to check again to see if the right is larger than the left, then we want it to replace that as well. So we always get the largest child sort of coming out on top, switching with the parent. So if right is less than length heap, and heap large is less than heap left, and bear in mind if this had swapped, then heap large would, I meant to put right there, sorry, then heap large would actually be heap left, so it would be then comparing if heap left was less than heap right. So this is a really neat little way of just carrying out that comparison within the logic of the script. Then large will be equal to right. So we've, in that little bit of logic, checked whether either of the children from their index position are larger than the parent. So if large is not equal to index, we know it's switched. We know that one of the children was bigger. And so we need to switch. We need to switch the child, and we'll do that same little bit we did before, which is heap index, heap large, is equal to heap large, heap index. So we just switch the values around. But that's not quite enough, because if we've done this change, we need to check if any child from that switch now also needs to change again. So here it is, when these two swapped, then we had 10 move down here and 48 go to the root position because it was larger. But we had this 21 here, which was clearly larger than the 10. So at the minute we've just done this swap. But we want to be able to check at this index position if any of the children need to now swap with this parent. And that's where we're looking at it as an independent bit, and we'll figure out that they need to swap. And if we had more children down here, we'd then need to keep going with this process. So what we're going to want to do is, it's actually super simple. We return it to the function of tidy heap. So we return it to this same function, and we give it the heap that we've got at the minute, where we've switched that index and large and index around. But instead of sending it just a generic index position, like the I position, we're going to send it the large position, so that it's going to have a look at the left or right child position, that index, and then work from there, and it can keep iterating down the heap. And then we'll just return heap. Now we'll want to save this, and we will generate a little array that we can test. So we'll have array is equal to, and I'll just put some numbers in here sort of randomly, 9, 2, 6, 3. There we go, just a nice spread of numbers. And we'll make test equal to heap sort array. We'll print the test out. cd sorting numbers, and then we'll use Python to call, what did we call this one? Heap sort.py. And there we go. If we have a look at our list of numbers here, oh, I always forget to print that out, but you can see it here. 10, 3, 1, 9. Well, we've got 1, 2, 3, 3, 4, 6, 9, 9. Yeah, there are 2 9s, 10, 12, 48. Perfect. So, there we have it. A relatively straightforward introduction to the heap structure for sorting, but I think this will bring to a close the sorting algorithms that we'll have a look at for the time being. So we've done a nice little selection of them. But if you enjoyed this one, please let me know. If you like this kind of content, subscribe, and I'll stop wittering now and probably have a cup of tea. See you later. Bye.